You know, everything you can see and touch, from the screen you're looking at right now to the most distant stars in the galaxy, it's all built from atoms. But have you ever wondered what atoms themselves are made of? Well, in this explainer, we're going on a journey to the very heart of matter. We'll be drawing from the foundational physics and Kahn's radiation therapy to really understand the fundamental structure of our universe.
Okay, so our journey starts with the atom. This is the fundamental building block of every single element. Think of it like this. It's the smallest possible piece of gold that's still, well, gold, or the smallest bit of oxygen that's still oxygen. Right at its center, you've got this dense, positively charged nucleus, and budging around it are the negatively charged electrons. It's this beautiful, simple structure that's the foundation for all of chemistry.
So how do we keep track of all these different atoms? Physicists came up with a really elegant shorthand. So X is just the chemical symbol, like H for hydrogen. Z down here is the atomic number. This is the important one. It tells you the number of protons, and that number is the sole thing that defines an element's identity. Then up top you have A, the mass number. That's the total count of particles in the nucleus, protons and neutrons together. We call them nucleons for short. This little code is basically a unique ID for any specific type of atomic nucleus, what we call a nuclide.
Right. So since we have protons and neutrons as our building blocks, we can start to classify atoms into what you might call a nuclear family, based on what's inside their nucleus. And this isn't just for fun. Understanding these relationships is totally key for things like carbon dating and medical imaging. So let's check out how they're classified.
Okay, this table really lays it all out. First up, you have isotopes. Think carbon-12 and carbon-14. They're both carbon because they have the same number of protons, but they have a different number of neutrons. That changes their stability, but chemically, they're the same. Then you've got isotones. They share the same neutron count. Isobars have the same total mass number, so the same number of total nucleons. And then there are isomers, which are really interesting. They have the exact same number of protons and neutrons, but one is in a higher energy state. It's like a coiled spring just waiting to release that energy. Getting these distinctions is absolutely crucial in fields from nuclear physics to radiation therapy.
So we've talked about the mass of all these little particles, but what if mass itself is just another form of stored energy? This was a completely revolutionary idea, and it's the key to understanding the incredible power that's locked inside the nucleus. The energy that powers the sun and our nuclear reactors.
Einstein basically proposed that mass and energy are just two sides of the same coin. The physical stuff of the universe is directly tied to its energy content. And this idea had, well, monumental consequences for how we understand the cosmos.
And here it is, the most famous equation in physics, right? E equals mc squared. It tells us that a tiny, tiny amount of mass can be converted into a tremendous amount of energy. Why? Because that mass is multiplied by the speed of light squared, which is just a ridiculously huge number. This is the source of all nuclear energy.
And to put a number on it, the energy locked up in just one atomic mass unit, that's roughly the mass of a single proton, is 931.5 mega-electron volts. So what does that mean? It means these tiny changes in mass that happen during nuclear reactions can release energies millions of times greater than any chemical reaction. Just think about that. Immense power is packed into the smallest particles in our world.
So we know the nucleus has protons and neutrons. But you know how it is in physics? Every answer just leads to a new question. Are these particles really the end of the line? Are they truly fundamental? Or is there another layer to reality hidden underneath? Well, the answer is no, they're not. So let's zoom in even further.
Now we're diving into the really, really small stuff, the truly fundamental particles, the things that, as far as we know, can't be broken down any further. This is the heart of what we call the standard model of particle physics, which is our best description of the subatomic world right now.
It turns out the entire universe is made of just two fundamental classes of particles. You've got fermions, which are the particles of matter. Think of them as the bricks and mortar of everything. And then you have bosons, which are the particles of force. They're the messengers that tell the fermions how to interact with each other.
So let's look at the fermions, the matter particles. They're broken down into two families, quarks and leptons. And what's absolutely incredible is that this small set of just 12 particles, plus their antimatter versions, are the fundamental building blocks of every single atom in the entire universe. That's it. That's the whole Lego set.
So, it turns out that protons and neutrons aren't fundamental at all. They're actually composite particles called hadrons, and they're made of quarks. It's a simple recipe, really. You want to build a proton? Just combine 2 up quarks and 1 down quark. A neutron? Easy. 1 up quark and 2 down quarks. That's it. This simple little formula forms the core of every atom.
Okay, so we've got our matter particles, the fermions. But how do they talk to each other? How does a proton hold on to an electron? How do those quarks stick together to even form a proton in the first place? Well, that's where the bosons come in. They are the carriers or the messengers of the fundamental forces of nature.
And here are those forces. You've got electromagnetism, which is carried by photons. It governs light and chemistry and all that. Then there's the strong force, carried by gluons, which is what glues quarks together inside protons and neutrons. The weak force is responsible for radioactive decay. And finally, gravity, which we think is carried by the graviton, though we haven't found it yet, is what shapes the entire cosmos.
Now, the Higgs boson is a special one. It's associated with something called the Higgs field, which basically permeates all of space. And as other particles move through this field, they interact with it, and it's this interaction, this sort of resistance to motion, that gives them mass. Seriously, without the Higgs field, fundamental particles would be massless, and atoms just couldn't form.
So we've gone from the atom all the way down to the fundamental particles that make up our reality. It's amazing, right? The whole universe is built on this simple yet incredibly elegant set of rules and particles. But it raises a pretty profound question. With this fundamental toolkit, what other cosmic structures and phenomena are still out there, waiting to be discovered?